In a normal year, I would start physical chemistry off with 2 lab lectures in the first 2 weeks. So instead of giving lab lectures, I'm going to make these 2 videos. This first video is on the beginning of error analysis. I talk about absolute and relative errors and what they are. And there are 2 examples, problem 1 and problem 2, that are on the handout that I posted on Blackboard called Error Problems. So this first video will talk about some very specific stuff about P Chem Lab, about lab reports, about how many there'll be, and I'll launch into some statistics, absolute relative error, problem 1, which is a very straightforward problem that many of you probably could do without me going over it. And then I'll talk about propagation of error, and then this video will end with doing problem 2 on that error problem handout. The next video, the next lab lecture, will start with some more, some other topics, including using Excel to do linear regressions and things like that. So this slide just introduces you to 3 handouts that have recently been posted. They were not posted right at the beginning of the term. One I call the syllabus, which lists the different labs we're doing and gives the type of assignment for each one, which is important. Then there's a handout that talks about information needed for writing reports and writing summaries. And then there's a treatment of experimental data handout, which is kind of like written down what I'm covering in these lab lectures, or at least part of it. And this is really our focus for today. And like I said, there are 2 error problems associated with this video that are called error problems and are also posted on Blackboard. Here is a summary of the types of reports you'll have to do and how many of each. There'll be 4 full reports, 3 involving calculations and other things. 1 is an assignment that's called problem 3, which I'll talk about in the next video. And it's worth half a lab. It's a pretty good deal. And then there's an extra credit assignment that I call the least squares assignment on Excel, which is worth 3 points out of 10 of extra credit. So it's also a pretty good deal. So you can see that there's 4 plus 3 is 7 lab reports, basically. 5 of those labs are for the in-person students, are wet labs, and 2 are dry for everyone. The chymotrypsinogen is a dry lab, and the isothermal titration calorimetry is a dry lab for everyone. So this slide talks about the different sections of a full lab report. And it starts off with a data section, but of course in 2020 with COVID, only the in-person students will include a data section. The online students will just have to tell me, show me in a page what their data was that I gave them. The in-person student should include a copy of their data, but it doesn't have to be signed because I didn't sign them this year. So in the summary, there are 3 sections. This is very similar to a summary that if you took general chemistry in this school, you will have had to do this. You write an objective, a method, and a conclusion. We basically use past tense. We mostly try to use passive voice, although if there's an occasional me or I, it's not a disaster, but you shouldn't have a lot of them in there. You should try to avoid the use of I. The method is the biggest part of this, and you must really get across how the experiment you do will allow for the desired quantity to be found. It's not always obvious in P Chem. It can be a bit of a story. So try to tell it concisely. Procedural information is part of the method section, but it is not all of it. So you really can't just tell me that you prepared 6 solutions or you watched the preparation of 6 solutions. You have to, basically give me the whole method of how making those solutions helped you to get to the answer. Please, no unnecessary details, and read the handout on this. It gives even more information. So when you do calculations, you need to give me a few words. You can't just write a bunch of equations and math. You have to say, calculating the molar mass or whatever it is you're doing. And if you have repetitive calculations, you need to use Excel or if you use some other spreadsheet, that's okay. But you're not supposed to do repetitive calculations by hand over and over again, not in P Chem Lab. So basically, you could show one sample calculation of each type, and for the rest, just put them in a table like an Excel spreadsheet. Do your calculations correctly. You know, this is really important. If you have questions, you need to get in touch with me, and we could have a nice Zoom session for you and me alone, okay? Sig figs really are important, but basically in PChem, a lot of times we use error analysis to figure out how many sig figs there should be at the end of a calculation. So sometimes we, go to more digits than we need to, and then the error analysis tells us how many sig figs we get at the end. You don't need to type equations and things like that in the calculations. It can be very time consuming as long as you write neatly and then take a good photo with lots of light and focused well, and incorporate that into your Word file or your PDF file that you hand in afterwards. In the discussion and conclusion, do not forget to state your results, because you will lose points for that. What numbers did you get? And if you have done error analysis, you need to put them as plus minus numbers. So, don't just tell me the answer, tell me what the error was. So, 52.5 plus or minus, 0.7, kilojoules per mole for a delta H or something like that. So give the obvious conclusions first. If you found a KEQ, give it to me. Then there are some less obvious conclusions. So for example, if you got a large equilibrium constant, say what that means, just like is written there. What would the sign of the delta G be? Was heat absorbed or released in the reaction? If so, what is that? Does it mean it was endo or exothermic? Does that sign make sense given the reaction that you were studying? If you obtained an entropy change, a standard entropy change, does that sign make sense? So don't go on forever, don't make stuff up, and don't copy stuff from the internet. Anyway, you're going to submit through SafeAssign. So if you did copy something from the internet or from a fellow student from a previous year, I would know about it. I definitely would. A lot of times I include questions or points of discussion. Use them, because that's what I'm looking for, okay? Usually this is about 1 page. Occasionally it's like a page and a half, double space, 12-point type. And there's an example in the handout for you to use. So the main focus today, as I said, is error analysis in P Chem Lab. And here's just a silly story, really. It's a true story. It's from when I was 7 months pregnant. I went to the doctor and I had an ultrasound. And I got the report, and it reported that the fetus, the baby, weighed 1905 grams. And I read that and I was like, wow, I'm really impressed, 1905 grams. Because, of course, when a scientist looks at a number like 1905, they think that the uncertainty is in the last digit there, in the gram unit. So the fact that it was reported to me as 1905 meant it was plus or minus a gram or something like that. And I told the doctor I was really impressed. And he said, oh, that's plus or minus 300 grams. And I was like, come on, really? Didn't you learn about sig figs in college? I didn't say that, I was too respectful, but really, if it was plus or minus 300, he should have reported as 1.9 plus or minus 0.3 times 10 to the third grams. But of course, that's not how it was reported. So that was something that I thought I should tell my students about, because it was outrageous to me. So I guess I start with the idea, the point of error analysis as being that measurements are almost meaningless if you don't know how well you know the answer that you get. So what we want to do in PChem is to figure out how big the error or the uncertainty is in the answer. And so how well you know the answer depends on, of course, what caused the error. So there's different kinds of errors in the PChem Lab. For example, operator error. So if you actually use an instrument and you use it incorrectly, you can get the wrong answer that way. So of course, we obviously try to avoid mistakes like that in the lab, and that's why, you have a professor telling you how to do something and showing you if you do something wrong. Then there are errors we call systematic errors that are, for example, if you use the wrong technique, Let's suppose you systematically blow out the last drop in a pipette, so you're always adding slightly more than you should be. You can be using equipment that is not calibrated properly, like a pH meter. If it's not calibrated, it could be off by a pH unit or more or whatever. And then there's the poorly designed experiment. Okay. So how do you even know if you have a poorly designed experiment? And the answer to that question is, well, that's why whenever you have a new experiment, you actually try it out on things you know the answer to before you do an experiment with something you don't know the answer to. So we experiment with knowns first. And that's how and then various protocols are developed, and if you always do it the same way, you won't get yourself into trouble. And there's lots of protocols in biochem labs and environmental labs, so where you really need to get the right answer. So you check it with knowns first before you do it with unknowns. But okay, so let's suppose you did that. You tried your experiment with knowns, you got the right answer, you have a well designed experiment, everything is calibrated well. Will you be able to get the exact value of a measured quantity? And the answer to that is no. Okay, and the culprit is random error. So there are always unknown, unpredictable variations in conditions, things like temperature, things like, air currents in the room, things like that. And the good news is that if the errors are actually random, you can estimate them, and you could really get a good idea of how well you know a measured value. So do random errors lead to incorrect answers? So if they're truly random, no, they don't. They just tell you what your uncertainty is. So you would generally get the same number of values above as below the mean. So the mean would really be unaffected. But you will get, like I said, a greater uncertainty. And this uncertainty determines how many sig figs you can report an answer to. And in P Chem Lab, we estimate the uncertainty, and then we use that uncertainty to determine the proper number of sig figs. So in P Chem Lab, generally, you can carry more sig figs in a calculation as long as at the end, if you do an error analysis, you round it to the correct number of sig figs and you express your answer to the correct number of sig figs given the error you calculated there. If you don't do an error analysis, then you just have to keep the regular sig fig rules. I think at this point in the discussion, I should go over the difference between accuracy and precision. So accuracy deals with how right or wrong an answer you get is. Okay, how close did you get to the true value? And you can find a percent error if there's a literature value that you can compare something to, an accepted value for a quantity. So you could basically find the difference between the measured value and the accepted value or literature value using the formula given here. Okay, but what I've been talking about in the last slide or two is really about precision, which is related to the magnitude of the uncertainty. And like I said, it has to do with random fluctuations. And it also has to do with the fineness of a measuring tool. So higher precision means there would be smaller fluctuations in the measurement. You'd have greater reproducibility. And that would mean your measurement really has more decimal places, more sig figs. So, for example, if you use an instrument where the fluctuation is in the 10,000ths place, okay, then maybe you'll get answers that are differ by 0.0001 if it's grams, right? The 10,000ths place in grams. That's pretty typical. If you use a balance that only goes out to hundredths place, then if you measure the same thing over again, you'd see fluctuations in the hundredths place. So greater fluctuations means poorer precision. Smaller fluctuations means greater precision. And we're talking about precision when we're talking about how many sig figs you get and how fine the tool is that you use to measure a quantity. Here's an example about just what I was talking about a few seconds ago, actually. So if you use a balance to weigh an object, and you weigh it as 10.24, okay, and then you weigh it on a finer balance, then maybe you'll get the number given there, 10.2387. So the assumption when you look at a value that you've measured is that the last decimal place has the uncertainty. The uncertainty is in the last decimal place. So in this particular case, you basically got the same value, just the second one is more precise because it's known to 4 decimal places, while the first one is known only to 2. So when we talk about errors, we talk about two different types of error, really just two different ways of expressing the error. So we have something called the absolute error, which is also sometimes called the plus minus error. It has the same units as the quantity. So for example, in that first mass, we'd have 10.24 plus or minus 0.01 grams. So the absolute error is plus or minus a tenth of a gram. So notice it has the unit of grams. It's giving you what the absolute error is that way. Relative error compares that error to the value of the quantity. So if you take that absolute error and divide it by the quantity, so 0.01 divided by 10.24, you get the number shown there, which we always round to one digit. So that would be called 0.001 or 0.1%. Okay. In the second example, the mass to more decimal places, you could see that it's 0.0001 over the 10.2387. So of course you have a much smaller relative error, 0.00001 or 0.001%. So the relative error is just taking the absolute error and dividing it by the quantity to say, how, what is the error relative to the value of the quantity. Now you can take a relative error and multiply it by the quantity and you will get the absolute error. And this is something that we use over and over again when we do error analysis in P Chem. So in the Physical Chem Lab, if you happen to do several determinations of one quantity, which we do in the 2-naphthol lab, we have 3 determinations in that lab. But I don't think we use this in any other lab. But what we do, of course, is we take an average, and that funny brackets around the X is a symbol for average. So all you do is you sum up the values, divide by the total. Everybody knows how to do that. And then below is an equation for the standard deviation. So what you do there is you sum the squares of the differences between the mean and the measured values. And the reason for the squaring of that is because if you didn't square them, then these errors could cancel each other if some were above or some were below the average. Then this is divided by n minus 1, which frankly, the reason why it's not n is something you would learn in a statistics course, not here. And then you take the square root of that. Okay, so that is a measure of the absolute error in a quantity. And in the P Chem Lab, when we do run across this sort of thing, we just use it as the absolute error. So we report the value as the mean plus or minus the standard deviation. So once you have a mean and a standard deviation, does this mean that you are sure that the true value lies between the mean minus the standard deviation and the mean plus the standard deviation? It's a logical question. Well, the answer is no, not exactly. What it means, though, is that if you took a huge number of measurements and the distribution function were a Gaussian, in other words, a perfectly symmetrical bell curve, then you could be 2/3 certain, 66.66% certain that the true value is within that range. Okay, so we won't be proving this here. You'd have to learn that in a statistics course. But anyway, I mentioned a distribution function, and these are worth talking about because we use them in P Chem, so they're used in statistics, but they're also used in physical chemistry. And a distribution function can be described as a function that shows the probability of obtaining a certain value of a property, x, as a function of that property. So for example, a height distribution for, say, men living in the US, the probability of a given height would be plotted on the y-axis, probability of somebody having a certain height. By the way, that's also the fraction of men that would have that height, and that would be plotted versus height. And basically what I've shown you here is a Gaussian distribution, which is very common in things like this, like heights in a population or stuff like that. And you might ask, well, how on earth do you get this curve? So what you could do is you could measure heights of men in the United States, and you could figure out what is the fraction of men having a certain height, like that's shown here, okay? So the first one on top would be if you didn't take that many measurements. And then as you took more and more measurements of men's heights, you would get a neater and neater looking distribution, and a nice smooth curve. So you don't have to measure the entire population, but you would have to measure a good deal of men's heights, okay? So that's a height distribution function. What this curve is showing is a Gaussian distribution, and it also gives you the mathematical form of that Gaussian distribution function. In the exponent, you see x minus average x, all squared. And that is why this curve is symmetrical about the mean. As x becomes greater than the mean or less than the mean, and that difference between x and x average increases, you get the same probability, and that's a lower probability than what this curve is at the maximum, which is at the mean. Because at the mean, x becomes x average, and x average minus x average is 0, and that is e to the 0 is 1, and that's the maximum value of this curve right in the center. So the mean is right in the center of a perfect Gaussian distribution function. The width of the curve tells you how well that mean is known, how well the measurement is known, okay? How the degree of uncertainty in your measurement. So if there's more scatter, there's going to be a greater error, greater uncertainty. That means there were more fluctuations. You have a wider curve. That's the curve on the right. The curve on the left must have been made with a finer instrument because it has a smaller scatter, and just smaller fluctuations in general. For a Gaussian function, the full width of the distribution at half the maximum, which is exactly what it sounds like, go down to half the maximum and look at the width of the curve. The full width at half maximum is twice the standard deviation. So the more scatter, the greater the standard deviation, the wider that curve will be. So getting back to the original question, can you be 100% confident that the range of the average plus or minus the standard deviation, that range contains the true value, and that the next measurement would be within that range? So now we can look at this in the context of the distribution curve. We could see that the mean plus or minus the standard deviation is the shaded area under that curve. And you could plainly see that there are parts under the curve that are not, that area does not include, okay? That there is plenty of possibility or probability of getting a value that's more than one standard deviation greater or less than what the average value is. So the question is, how confident can you be? And the answer is that as that number of measurements gets really, really large, approaches infinity, you can be 66.666% confident, or 2/3. We'll never be able to get an infinity of measurements, obviously, but the more measurements you make, the better. So the greater the number, the smaller the range for a certain level of confidence. That is to say that more measurements increases confidence. It also still depends on the standard deviation. Obviously, the greater the standard deviation, the more uncertain, right? So that means to be a certain level of confidence, you'd have to have a greater range. And then it depends on what your level of confidence that you want is. Do you want to be 67% confident, or do you want to be 99% confident? If you want to be 99% confident, then you're going to have a much wider range. And here's the other thing it depends on, is the shape of that distribution curve, which is only a perfect Gaussian if you have an infinite number of measurements. Okay, so what we do to compensate for this is we use something called the student's t-value. And I give you a table of these t-values in the treatment of experimental data handout. And so this t-value is combined with the standard deviation and the number of measurements to give you the confidence limit range. So I'll show you an example of that when we do problem 1, which I'm going to do next. So here is problem 1 of the error problems. It's on the error analysis problems on error analysis handout. And I'm sure you've done a problem like this before in your life. Here's some data for the mass and the volume of copper. Okay, so so we have basically a copper block, and its mass was determined by 4 different times. So it was basically placed on the balance 4 different times, and its mass was measured. And then its volume was measured by water displacement, also 4 different times. And these are the values that were obtained for the mass and for the volume. So the first question is simply to find the average mass and the average volume, then find the standard deviations in mass and volume, and then round these standard deviations as absolute errors to one significant figure. And I'm going to show you how to do this part on Excel before we get into the rest of the problem. So let me go over to Excel. And you can see here that I have the masses here in this column, first column, all right? And I have the volumes here in this column. And so to do the average, I don't ever want you to do this by hand. You would simply type equal average, parentheses, and put the range in, okay? So I just I clicked and highlighted that range. I hit return and it calculates the average for me, okay? And to do the standard deviation, STDEV, paren, the same, click and drag. Oops, something went wrong there. Oh, I know, I forgot to put the equals. Let's go over here. Equal, standard deviation, and then the range in here. Close parentheses. So that's the standard deviation. And again, here I'm going to copy this formula into here. So it's going to give me, see here the formula, it's giving me the average. And I'm going to copy this formula here. Okay, but it's going to give me the standard deviation of these. Now, write the mass, and so that's number 1. Find the average mass and the average volume and the standard deviation for mass and for volume. And we did that using Excel. Although I could copy these down here, really, I should have done it here. I'm copying just the values. Okay, so I just repeated them there. So in P Chem, what we do is we generally round the errors to one significant digit. So, and then, so here I'm going to draw. Here's a pen. Okay, good. Maybe I'll get a red color if I could find how to do that. Okay, good. That's good. All right. So what I would do is I would have to get rid of this thing. I would round my standard deviation to 1 digit. Okay? And this one would be, well, actually I want to write it down here. This is 0.1. Now, if it was 0.15, I might leave the 5, or 0.14. So if it's between 4 and 6. But if not, these are basically estimates of errors, so I'm not going to express it to more than 1 digit. So how would I express my answer here? So here's my average. So my mass would be 25.7632 plus or minus 0.0003. So This tells me that I have an error in the fourth decimal place, and so I cannot report to greater than the fourth decimal place. That's what we always do with errors. We round that. We basically round them to one sig fig, unless there's like a 4 or a 5 or a 6 after, in which case you could keep a second one. And then you don't go beyond this number of figures in the number that you're reporting, okay? For the volume, well, the average is 2.86, and now the error is 0.1. Ooh, what am I going to do there? Looks like my error is in the first decimal place, so I can't express this to the hundredths place. I am going to have to change this to 2.9 plus or minus 0.1, and that is how I would report the volume if it was my final answer. If I'm going to go on and make a calculation from the volume, I might keep an extra digit. Okay, so let's answer this question here. It says, why use one sig fig for errors? It's because they're estimates. So why go crazy with an estimate? If the second digit is near 5, like if it's 4, 5, or 6, you can keep 2 sig figs in errors. Okay? Now, here's a very big question, I think, a very important question. Could the volume really be measured to the nearest 0.01 milliliters? So you see how I have the volume here to the nearest hundredth of a milliliter. But this is my standard deviation, and this shows that there's fluctuation in the tens place. So honestly, I really wasn't able to, if I was really able to read that volume to the hundredths place, then I would see the standard deviation would be in the hundredths place. So here the fluctuations really tell you what the error is, and it tells you that the error is in the tenths place. Okay? So now it goes on, it says find the density for each determination. This is number 4. So I can easily do that in Excel. Go here, I'm going to go equals this divided by this, and there's my number. I'm going to copy it because I like the same thing here. And you can see it gives you all kinds of crazy significant figures, but now I'm just going to find the average, so I'm just going to copy the average formula, and then I'm going to find the standard deviation again like this. Okay, so find the density for each, find the average density and the standard deviation. So I've just done that. So now I can say that the density is, so I'm going to write my average, 9.02 plus or minus 0.36. Now there's something wrong with that, okay? I don't know why it doesn't want to stay here, okay. But what's wrong with it is that I cannot report, first of all, I could keep this because it has a 6, but really my uncertainty is over there. So I would report this as 9.0 plus or minus 0.4, or I could say 9.02 plus or minus 0.36 and keep the hundredths because I have the hundredths place there. So either of those ways are acceptable ways for me to express this answer. Okay. That would be grams per milliliter. Okay, so now let's go to the next one. Well, first of all, comment on the precision of the density. Well, by that I mean, you calculated the density based on a mass that had many, many sig figs and a volume that had 3 sig figs. You might have expected that the density would end up having 3 sig figs. But in fact, we end up with a density that's 2 sig figs because we use the error, the 0.4 there, to estimate that. Okay, the only reason I'm showing this is another alternate way of doing it, but you could still see that the uncertainty is in the tens place, and you really only have 2 significant digits here. So just because you have numbers that appear to have a certain significance, you have to look at the fluctuations as is reflected in the standard deviation. So the standard deviation is a pretty big help when it comes to figuring out how well you know a number. And now the question, which is more precise, the mass or the volume? Well, oh, and I should write this here, by the way, 9.0 plus or minus 0.4. Or you could express it as 9.02 plus or minus 0.36. But I personally think it's a little silly to go to a hundredths place when there's error in the tenths place. All right, so which is more precise, the mass or the volume? Well, what you would do here is you'd calculate what I call a relative error. So you would take the plus minus error, so for the mass, you take 0.0003 and divide it by 25.7632. Okay. And you get 0.00001. That's pretty small. That's 0.001%. So it tells you that the standard deviation is 0.001% of the number, and that's for the mass. But for the volume, now you have 0.11, right? There's the standard deviation. 0.11 divided by the value of the average, which was 2.86. And when you calculate that, it's 0.038. So that is actually 3.8% of that's what the standard deviation, this is S over the average. S over the average, okay? So you could see the volume has a much larger percent error, so the volume is less precise, okay? Much less precise. And what about confidence limits? Okay, so I'm going to talk to you about that. Confidence limits. So let me go back to OneNote for a sec. Okay, we did actually 2, 3, and 4. We did that on Excel. And now we're up to the confidence limits. And we have this crazy formula. If we want to find the 95% confidence range, so in other words, we find the range that we could be 95% confident that the true value is in there. So we're going to find lambda 95 and lambda 99. This is for 95% confidence. This is for 99% confident. So lambda 95 is this t value, 95 times s over the square root of n, and n is the let's see, right, n is the number of trials, number of times you did the measurement. Okay, so there were 4, so n is equal to 4. Okay. 99, we have to use the t value for 99% confidence. So those are the formulas that we're going to use. And let me show you the table now. So this is the confidence level table. These are the t values. Okay. So it's a little crazy here, right? Because we use n in the equation before, but this is actually something that's called the degrees of freedom, which is actually not n, it's n minus 1. So 4 minus 1 is 3. So our T95 is this number here, and our T99 is this number here. So to calculate our lambda 95, that was T95 s over the square root of n. So that's 3.182 times s, which was 0.36. This was for the density, divided by the square root of 4. So that comes out to 0.56, which I'm just going to call 0.6. So that means that 9.0, the average density, plus or minus 0.6 grams per milliliter, that is the density to 95% confidence. If I want the 99% confidence, I'll have to take T99 S over root N. T99 is 5.841. You can see it's going to be a lot of a wider range because I want to be more confident. Okay, and this comes out to 1.05, which I'm just going to round to 1. And I'm going to write the average 9. I can't do, look at this. I can no longer express this with the tenths. I'll have to express it 9 plus or minus 1 grams per milliliter. So what I'm showing you here is that if you get an error estimate, to a certain, it goes to a certain decimal place. Like, let's suppose you have 7.423 plus or minus 0.02. You can't express it this way. You can't express it to more than the decimal place that the error goes to. Like, so you have an error in the hundredths place. So you can't express the value to more decimal places than the hundredths place because you don't know anymore. You don't know beyond the hundredths place. So you'd have to express this as 7.42 plus or minus 0.02, whatever, grams per milliliter or whatever unit it is. So students all the time are telling me answers like, 5.756 plus or minus 0.1. That's just not right. You'd have to say 5.8 plus or minus 0.1. That would be the right way to express it. So use the error estimate to determine the sig figs of your answer. So this is pretty important. Okay, so I'll put a couple exclamation points there. All right, so that is problem 1. I'm done with that. Actually, no. I think there's more, it turns out. Number 6. So what is the percent error compared to a literature value? And getting back to our density example, we had 9.0 plus or minus 0.4 as our answer. And the percent error compared to a literature value. So it's saying, what if the literature value is 8.92? So we would take our value minus the literature value. It doesn't matter. We're going to take the absolute value, so it doesn't matter which way you do this. And divide it by the literature value. And multiply it by 100 to get the percent. And that comes out to 0.9%. Okay, so that's how you do that type of calculation. So was the measure of density accurate? Well, is it consistent with the true value? So I would say yes. The true value, which we happen to know here, we don't always know it, is within the confidence range, right? It's with 9.0 plus or minus 0.4. That's the standard. Using the standard deviation, it's actually within that range. So I'd say not a bad job. You can't really, you can't do better than put it in that range. Now, what if, supposing I measured 8.3 grams per milliliter instead of 9.0. Okay, that's outside the range. And then I may have to look at the experimental setup, and maybe I'll find a problem. So it indicates some kind of systematic or operator error. Possible. This next section of the video is about propagation of error. What to do if you don't have many determinations of something that you've measured. So this section has to do with what you do if it's impractical to do several measurements in the lab. So how do you estimate the error in a case like this? So what you do in that case is you can estimate the error based on the measuring devices and some common sense. So for example, if you have a balance that measures to the nearest 0.0001 grams, you could take the error to be plus or minus 0.0001 or 0.0002. Those are reasonable estimates. Most pipettes are calibrated to the nearest plus or minus 0.01 milliliter, but perhaps most people don't use them to that precision. But you could use plus or minus 0.01 or plus or minus 0.02. Similarly, when you have markings that, like for example, the thermometer, what we generally do is if they're marked to the tenths, we would take 1/10 of the smallest division, which would be hundredths. Similar, like if you used a burette and you read it to the nearest hundredth, you would take, they're marked to the nearest tenth, you could read them to the nearest hundredth, you would say your error was plus or minus 0.01 or plus or minus 0.02 milliliters. But suppose you have error estimates for all of the things that you use in your experiment, your volume, your mass, whatever it is. What do you do when you make calculations? Okay, so when you calculate something from measured values, you have to do something called error propagation, where you propagate those errors through the calculation. So how do we propagate the errors through a calculation? Where do we go to see how errors, meaning a small change in, for example, if you're calculating the pressure, a small change in mass or volume, how does that lead to an error in the pressure that you say calculated from those things? And this is a very interesting application of that formula that I taught you about, or at least a video I made taught you about it, about the total differential of a function of more than one variable, df, and how it equals slope in the x direction times a change in x plus the slope in the y direction times a change in y. And here those changes are the errors in x and the error in y. So here it is. Here's what I was talking about. If f is a function of x and y, we've learned about this equation here. df is partial f partial x dx plus partial f partial y dy. But now what we're talking about is what is the error in the function, the small change in the function, if the x and y values are changed a little bit, if there's errors in them. So the error in x would be delta x, the error in y would be delta y. So what we're going to examine first is what happens if f of xy is just the sum of x plus y. How is the error in function related to the error in x and the error in y? How is the error in the sum related to the error in the two things that are being added together? Okay, that's what I'm going to address next. I'm going to use OneNote to do it. If the function f of xy is the sum x plus y, how does the change in the function relate to the change in x and the change in y? So the first thing to do is to calculate these partial derivatives, which are pretty easy in this case. So the derivative of f with respect to x is actually 1, because it's just the derivative of x with respect to x, because we hold y constant for that derivative. And similarly, the partial derivative of f with respect to y is also 1. Well, that means that df is 1 dx plus 1 dy, okay? So that means that delta f, in, basically df becomes that, is delta x plus delta y. So what this tells you is that the absolute error in a sum is the sum of the absolute error in x and the absolute error in y. So so this delta x and delta y, they would be like if you knew x was x1 plus or minus delta x. This is the absolute error in x. And if you knew y was y1 plus or minus delta y, this would be the absolute error in y. So that gives us one of our error propagation rules. Okay, let's go to another one. Suppose you have a product. Okay, so suppose your function is a constant times x times y. Then how does the df relate to dx and dy? So for this function, the derivative, or the partial derivative with respect to x, is just the constant, which is a times y. A times y times 1, right? You put the constants in front. This would be a x y. So if you're taking derivative with respect to x, you might write it this way. And the derivative of this with respect to x is just a constant. Similarly, df dy, you do the same thing, but maybe you'd write it as ax y. Okay, the derivative of this is the constant times the derivative of the function, so it's just ax times 1. So df is ay dx plus ax dy. Where are we going with this? So that means that the delta f, because we're changing these to deltas because you can't measure differentials. Okay, so we have ax delta y. So now what I'd like to do is I'm actually going to divide both sides of this equation by the function. And remember, f is ax y. So you could see what happens here is that the y's cancel and the a's cancel. And here the x's cancel and the a's cancel. And you end up with delta f over f equals delta x over x plus delta y over y. And this is phenomenal. Because remember, this is the absolute error in the function. That's the plus minus error. If you take that and divide by the function, that's the relative error in the function. And that's equal to, well, this is the relative error in x plus the relative error in y. Isn't that nice? Great. And the reason it's so nice is because it tells us that the relative error in a product, so xy is the product, is the sum of the relative errors in the factors. Okay, here's the relative error in the product, sum of the relative errors in the factors. Okay, so that gives us our second rule for error propagation. So here's the first error propagation rule. Like I just said, when adding or subtracting, the absolute error of the sum is the sum of the absolute errors in the quantities being added or subtracted. So that's what I'm showing you here, how you see I've added the 0.2s to get 0.4 as the error of the sum. And then now we have the second of these rules, and that is for when multiplying or dividing, the relative error in the product or quotient is the sum of the relative errors in the quantities being multiplied or divided. So for example, if you're finding an area and you know the length and the width, and you know they each have an error, which is expressed there as their absolute error, plus or minus 0.4 for each one. First thing you have to do is find the relative error in the length and the relative error in the width by dividing those absolute errors by the quantity. So 0.4 over 11.2 for the length and 0.4 over 10.3 for the width. And you can express these as a percentage if you want. It's not necessary, but you have to add those relative errors, and you'll get 8% for the relative error in the product in the area. Okay, and so now when you want to find the absolute error in the area, you have to convert that 8% back to an absolute error by taking 8% of the number. If you didn't convert it to a percent, it would just be 0.08 times that area, 115.36, and you'd get 9 square centimeters. So you would not express the area as 115.36. You'd acknowledge that you have an uncertainty in the ones place, so you'd express this as 115 plus or minus 9 square centimeters. Or you might even say, well, 9 is so close to 10 that you might express this as 1.2, rounding to the tens place, times 10 to the 1, plus or minus 0.1 times 10 to the 1. In other words, 120 plus or minus 10, but you would express it in scientific notation, and you would always put the error and the quantity with the same power of 10. Okay? And notice that the absolute error, again, determined the sig figs that you had. So now we're ready to tackle problem 2 of the error problems. So this has to do with a lab where that is often done in general chemistry, where the molar mass of a gas, in this case the gas is butane, but it's generally an unknown gas. We don't tell the students what it is. So then they find the molar mass by measuring the mass, volume, pressure, and temperature of a sample of gas. And if you did this lab experiment, you might remember that there's a canister, and then there's a pan of water with an upside down graduated cylinder. The water goes all the way up at the start, and then when you take and you push the gas through this tube, and then the level of the water goes down, and so here's the water, and then here's the unknown gas, and you do various things. You measure the canister before and after. You're able to find the pressure and the volume. But this part of this exercise is really not about how you calculate it so much, but how you handle the errors and even how you estimate the errors. So this is just describing the experiment that I just described, and this is giving the results. So this is the mass before, the mass after, the volume, the pressure, and the temperature of the gas. Okay, so the goal is obviously to find the molar mass, but our ulterior motive is dealing with the errors. So I'd like to walk you through estimating the absolute errors. So for the mass, an analytical balance was used, and it read to the nearest 10,000th of a gram. And, generally there are some fluctuations in the value of the last digit. So you could say plus or minus 0.0001, but probably plus or minus 0.0002 is gives you a better idea of what these fluctuations actually are. So I would go with that. And I know it's not until number, 2 that we find the mass, but I'm going to do it now. So we have 10.4889 plus or minus 0.0002 grams. That's the initial mass, and then we're going to subtract the 10.4297 plus or minus 0.0002. So, obviously we subtract these numbers here, we get 0.0592, but we add these because that's the rule. When you subtract or add, you add absolute errors. So this is a subtraction. So we add them, we get 0.0004 grams. I do want to tell you that normally, and I think this might be a good idea, is you may want to go through this by yourself, see how far you can get before you run into snags. Because a lot of times I have my students do that, and they learn a lot from it. So here now we have the mass with its absolute error. Okay. Now let's deal with the volume. Okay, so what it says is that a 100 milliliter graduated cylinder was used. So these have divisions every milliliter. Okay, it's marked off every milliliter. So what you generally do is you take 1/10 of the smallest division, and you're expected to estimate that last figure. Okay, so 1/10 of that smallest division is 0.1. So plus or minus 0.1, well, I think that's a little optimistic. So I'm going to make it plus or minus 0.2. So that sort of thing is allowed. Okay, so the volume was 26.2 milliliters. So it's 26.2 plus or minus 0.2 milliliters. Okay, so that is the volume with its error estimate. Moving along to pressure. The pressure, okay, so you're reading a height of a mercury column and a barometer, right? I would say optimistically you should be able to read to the 10th of a millimeter. Well, you know, there's actually a vernier scale which helps do that. It's a mechanism, it's a scale that helps you read that last digit, but that's pretty optimistic. So I'm going to go with plus or minus 0.2 millimeters. So let's see, we had 757.0 plus or minus 0.2 in torr. 757 divided by 760 is 0.9960 atmospheres. We'll deal with how to find the error in atmospheres a little bit later. Okay, so now the temperature. So thermometers, they're, say, calibrated to the nearest degree. It's not so hard to read the tenths place. So let's take it to be plus or minus 0.1. So we have 26.4 plus or minus 0.1 degrees C. Okay, and of course you'd have to add 273.15 to that. Cut off 299.6 Kelvin. Okay, so here we go. All right, we'll deal more with the errors in a little bit. So now let's calculate this. We did this already, the mass of the butane. Let's calculate the molar mass. That's MRT over PV. This is just a straightforward Gen Chem calculation. 0.0592 grams, 0.08206, 299.6 Kelvin divided by 0.9960 and 0.262 liters to convert that to liters. My units go. I end up with grams per mole like I should, and it comes out to 55.76 grams per mole. And even though I have 3 sig figs here, I should only keep 3 here. I'm going to keep all the sig figs, and I'm going to let the error analysis tell me how many sig figs I really have. Okay, so we're going to go through that. All right, now this formula, everything is being multiplied or divided. So we're going to end up adding, we're going to have to add, we're going to find the sum of the relative errors in M, R, T, P, and V. And when we add that up, that will equal the relative error in the molar mass. Okay? So we have to find the relative errors in these things. So the relative error in the mass, okay? The mass was 0.0592 plus or minus 0.0004 gram. So we're going to take 0.0004, that's the absolute error, and divide it by the quantity. Obviously, grams are going to cancel. Relative errors have no units. This comes out to 0.0068, which, you could keep those two figures in your calculation of errors, or you could round it. If you're going to convert it to a percent, 0.7% or 0.68%. Okay. Now the relative error in the volume, we have 0.2 milliliters. Sorry, let me just rewrite it. We have 26.2 plus or minus 0.2. So our absolute error is 0.2 milliliters over the quantity is 26.2 milliliters, and so it comes out to 0.0076 or 0.008, okay, or 0.8% or 0.76%, the way you want to do it. So once we have the relative error in the volume, I want to make a comment, right? And it's important because the quantity that actually is used in the calculation is liters. So we know that the relative error is 0.8% or 0.008 in milliliter units, but what is it in liter units? So how do we handle unit conversions when we're dealing with relative error? Okay. So here's the thing. What are you actually doing when you convert, for example, milliliters to liters? What you're doing is you're dividing by 1,000. So it's a division. Or you're multiplying by 1 over 1,000, okay? It follows the rule for multiplication and division. So you would take the quantity, divide it by 1,000. So that means you would add the relative error in the quantity, which is the thing we've calculated over here already, 0.8%, plus the relative error in 1,000, the conversion factor. Well, this is exact, and basically all conversion factors don't affect the significance. They're all considered to be pretty much exact, or so precise that you don't even have to bother with it, okay? So basically what this means is that the relative error in the quantity in milliliters is equal to the relative error of the quantity in liters. Okay, so I can say this is 0.0262 liters, and the relative error is also 0.8% or 0.008. Okay, and I have a little slide to show you that. And so this is all about converting from one unit to another. So it says when you're doing unit conversions, a quantity is converted using a conversion factor. And that this usually, not always, but usually the conversion involves multiplication or division by the conversion factor. But generally the conversion factor, as I said, is either exact or one with many significant digits, so it has no error. Okay, so if you're converting torr to atmospheres, for example, you're dividing by 760 torr per atmosphere. That's a conversion factor. And here's the value in atmospheres, but the error, the relative error in the pressure in atmospheres is the same as what it was in torr. Okay, and that's because you're adding the relative error in 760, but 760 is considered exact. It's a conversion factor. So when you have most conversions, most of them involve multiplication or division, the relative error in the converted quantity is just the same as the relative error before conversion. And now I'm going to show you the one thing that isn't, where this isn't the case, and that's for temperature conversions, because these are weird addition conversion, where you're adding 273.15 to go from degree C to Kelvin. So how do you do an error conversion there? But before I do that, I'll just, oops. Yeah. All right, what's going on here? It's down here. I did this. So now I just want to go over the pressure. So here's the pressure in torr, okay, and it has a relative error of 0.03%. But that means that the relative error in atmospheres is also 0.03%. So the conversion to atmospheres was done earlier, and that conversion comes out to 0.9960, and it has a relative error of 0.03% also. Okay, we'll be using that in our error chart that we do next. But there is one other strange conversion. Strange because it's an additive conversion. Okay, so we had that the temperature in degrees C, so we had that it was 26.4 degrees C, so 26.4 plus or minus 0.1 in degrees C. Then we added 273.15. We get 299.6 Kelvin. Now the relative error, so when you add these, this has 0 absolute error. So when you add these two numbers and you get your temperature in Kelvin, the absolute error in the sum is the absolute error in the temperature in degrees C plus the absolute error in 273.15, which is 0 or negligible. Okay, so when you get this 299.55 Kelvin, the absolute error is still 0.1 plus or minus 0.1 in kelvins. Okay, so it's a really, really small error. You would take 0.1 over 299.6, and that's how you would get the relative error of 0.0003 or 0.03%. Okay. All right, so that's the different one. That's the weird one because it's an additive conversion. So you might think you'd have an error that was like 0.1 over 26.4, but, well, really it's not. It's 0.1 over 299.6. Okay, what we do with all of this is we put it in an error chart. So I'm going to fill this error chart in, and most labs that require error analysis like this require you to make such a chart. Okay, so let me tell you, okay, we had the mass of the canister was 10.4889 grams. Grams is there. The plus minus error, 0.0002. Then we had the mass after the gas was dispensed from the canister. It's a smaller mass. Again, it has the same absolute error. The difference is 0.0592. That's the mass of the butane in grams. But now we add these to get this, plus or minus 0.0004. Okay, so that's the first thing. Now, the reason for having a column for relative error here is because when we calculate the final answer, okay, we're going to want to add the relative errors of all the factors. So we had M is MRT over PV. So this mass here is the mass of the gas that was dispensed. It's this mass. So the only thing we need the relative error of is the circled mass, not those other masses, because they won't enter into this calculation. So we only calculate what we need on this chart. And if you take the 0.0004 and divide it by 0.0592, which we already figured out was 0.7%, and that's what we put there. Okay, and you could take it to 2 sig figs if you want. A lot of times I do that, because a lot of times I do these calcs on Excel, and you can't stop it from doing that, so why? The volume was 26.2 milliliters. Okay, I have a milliliter unit here. And it's plus or minus 0.000, sorry, plus or minus 0.2 milliliters. And when you take 0.2 divided by 26.2, you get 0.8%. Now, when that's converted to liters, all you need to do is recopy this. Okay? And there's no need to calculate this because you don't use it in the error calculation. The pressure in atmospheres, 0.9960. Oh, sorry, the pressure in millimeters, 757 with an error of plus or minus 0.2. We calculated this to be 0.03%. In atmospheres, it's 0.9960, and we don't need this. We only need the relative error, and it's the same because it's a multiplicative conversion or division conversion. It's not an additive one. The temperature in degrees C was 26.4 plus or minus 0.1. And now I don't need the relative error in the temp in degrees C. I need it in kelvins. The Kelvin temperature is 299.6. This is the same because you're adding this plus or minus 0.1 to the error in 273.15, which is 0. So this is the same. And now I'll find 0.1 over 299.6, and it's a very small number, 0.03%. Okay? And now, okay, so where's my factors and divide things in this equation, right? So the relative, I'm going to need to add the relative error in M plus the relative error in, in R. What is the relative error in R? That's the gas constant, right? That's equal to 0, okay? Those famous constants are known to many sig figs. We use them to more than we usually have for everything else. So we're going to have to add the relative error in M, the relative error in the temperature, the relative error in the volume, and the relative error in the pressure. So here is the mass. We're going to add this. Okay, now we're not going to add both volume errors. We're not going to add it in milliliters and in liters. We're just going to add it in the unit that we used, liters. We don't want to count it twice. We're going to add the relative error in the pressure and the relative error in the temperature. So I'm going to add all of those, 0.7%. Or if you took it to more sig figs, that's fine. Usually I do. 0.03 and 0.03. If I add that up, I get 1.56%. And then, so this becomes 1.56%. And then to find this, I find 1.56% of this quantity, which we already calculated. Remember, we got 55 point something. I think it was 0.76. Let me just make sure I get that right. Yeah. But I'm not writing that in yet because I have to take my 1.56% of 55.76 to get the absolute error. And that comes out to 0.9. So that's my absolute error. So this, now I realize I can express this to only the tenths place in grams per mole. So 55.8 plus or minus 0.9. That's how we'd express the answer in grams per mole. And that's how you do a fairly simple calculation like this. If you wanted to call it 56 plus or minus 1, this is almost 1. That's okay. All right, but you do not call it 55.76 plus or minus 0.9, right? You can only carry it out to the tenths place. So let the error in the calculated quantity determine the number of sig figs that it has. Okay? So that's how you do it.